We're going to continue on with the prerequisite section 3. This is part 2, functions and their graphs. At the end of part 1, I was talking about the different graphs you should know without a calculator. So for instance, y equals x squared, y equals x to the third, etc., etc., etc. If you didn't watch that video, you're going to want to go back and watch that video. Those graphs were at the end of the video. Okay, so now what we're going to do here is we are going to take those sort of standard graphs and we're going to get all sorts of new graphs by doing shifts and reflections and then some dilations down here. So you want to get this in your notes here. So all of these are the things you can do to sort of change the graph, change the shape, shift them, etc. So the first is if you take x minus c and plug it into f, you're going to shift that original function c units to the right. Okay. If you plug into the function x plus c, you're going to shift that original function c units to the left. Okay. If you take that function and subtract c on the outside of that function, it's going to shift that original graph c units down. If you add c on the outside of that function, you're going to shift the original graph c units up. If you have a negation in front of the function, you're going to reflect f over the x-axis. If you have the negative plugged into the function, negative x, you're going to reflect f over the y-axis. And finally, if you have some value in front of f, first of all, it depends what that value is, whether it's greater than 1 or between 0 and 1. Essentially what it's going to do is it's going to take all those outputs, those y values, and it's going to multiply by whatever a is. So if a is greater than 1, and this is sometimes referred to as a dilation, if a is greater than 1, you get like sort of a stretching effect. The points don't move this way or this way. It's just that for each x value, we multiply that value. So for instance, if a is 2, all those points double their distance from the x-axis in both directions, both negative and positive. And we'll take a look at some examples of this. This one tends to be the most confusing. These are usually pretty easy. And then if you have a fraction, right? So if you have a value a that's between 0 and 1, it's actually, those y values are going to move closer to the x-axis. So I'm calling the moving away as a stretch, and this is a squash. These are not math terms, obviously. It's just a way to sort of describe what's happening. So for instance, let's say a is 1/2. Those values on either side of the x-axis will move half the distance to the x-axis that they were before. Okay, so that is how we're going to manipulate these functions. So let's take a look at a couple of examples of what that's going to look like. Okay, so let's say we had a function, start pretty basic, a function f of x equals the absolute value of x minus 1. Okay, so first of all, we want to look at the parent function. So the parent function in this case is just simply f of x equals the absolute value of x. Take a look at what that looks like. And basically, you know, this is something you can do, you don't have to do. Sometimes people will draw this original graph and then erase it. It's really what works for you. I personally, you know, maybe in previous classes you had to show all this manipulation. In this class, we're just ultimately what I'll be interested in is that graph. Okay, so what's happening here is, so this is my parent graph. As I showed you before, this is the x minus 1 plugged into the function itself, right? So what's going to happen here is all these points are going to shift 1 to the right. So this point will move here, 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 and this point will move here. Okay, so our function in pink is going to look like that. So it's the parent graph shifted 1 to the right. Now, if you sort of do that as dotted, or if you want to go back and erase, so we don't get confused, that's the graph that we were originally trying to graph. So, yesterday or on the other video, we looked at, I can't remember exactly how many graphs there were, like 8 or 9. So with these different shifts and things like that, there's literally an infinite number of possibilities you could get. And it's going to give us an ability to take a look at graphs without a calculator, and pretty easy. Obviously a lot faster than plotting points. Okay, so let's do 2 more. So let's do let us do f of x equals negative x squared. This can sometimes confuse folks because this really is a function that is doing 2 things. So we have the negative out front, which is going to cause it to reflect over the x-axis, and then we're adding 2. We actually apply the reflection first. Okay, so let's start with the parent graph. Let's do the parent graph separate, just to keep track of this. So our parent graph, f of x equals x squared. Oops, no, not that point. Looks something like this. Okay. So what we're doing here is there's 2 things happening. First of all, we're taking this original graph and we're going to reflect it over the x-axis. And however much you need to do, if you need to do each step at a time, that's up to you. If you can kind of do this all at once, that's fine as well. Whatever you need to do. Let's do that. Dotted. Okay, so this is right here is f of x equals just negative x squared. So now the graph that we're interested in right here, we're just taking this graph and shifting it up 2. Right, so we're going to take all these points and shift it up 2. So this point right here goes to 0, 2. Okay, this point at 1, negative 1 goes to 1, 1. And on the other side, negative 1 goes to negative 1, 1. This point here, 2, negative 4 will be 2, negative 2, and on the other side, negative 2, negative 2. And that is our new function with the reflection and the shift. Okay, so pretty straightforward stuff. All right, let's do one last one. And this is one that can cause the most confusion in different contexts. Okay, so this one is the dilation, the value in front. So let's go with f of x equals 2 times the square root of x. So let's start with the parent function. F of x equals square root of x. Once again, I just want to remind you that we don't need a ton of detail, but you have to show sort of the most pertinent points and where those go. If it's unclear, that's when we're going to have an issue. But in general, sort of a sketch is perfectly fine. Okay, so this is f of x equals square root of x. The important points, we have that endpoint there at 0, 0. We have this point here at 1, 1, and this point here at 4, 2. Okay, so now what we're doing here is, when I talk about a stretch, what this is meaning is all of these values, these y values, get multiplied by 2. Okay, so Okay. Now, if this is below the axis, they're going to move farther away. If it's above the axis, it's going to get pulled closer. So the point is, any points around the x-axis aren't going to change. So at 0, 0, you multiply 0 by 2, it's going to stay 0. Now here, 1, 1, okay, that's going to, the x value doesn't change, just the y value. So that 1, 1 goes to 1, 2, okay. The value we had at 4, 2, okay, is going to get multiplied by 2, so that's going to end up at 4, 4. So we get a graph that looks like that. So that's why I called it like it's like a stretch away from the x-axis. Okay. Now let's say that we have, let's just get a different color here. Let's take that same, let's do this. Let's do a semicircle. Semicircles can be kind of strange. So let's say we have y equals, let's go with 1/2. Okay, and let's go 16 minus x squared. Okay, so a semicircle, so let's start with the parent function, y equals square root of 16 minus x squared. So the semicircle, we take the square root of this number, and that's going to be the radius. So that's going to be 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Okay. So we get something that looks like this. Okay. All right. So now, if I have the 1/2 in front, all of these y values get multiplied by 1/2. What's important is sometimes people think of a squash, those values are going to move out. They do not. Remember, those 0 values will stay put. Okay, so multiply that by 1/2, it's staying 0, and that's also true on the other side. What happens is all these values get multiplied by 1/2. So for instance, if you just look at this value, it was at 0, 4, now it's going to be at 0, 2. And that pretty much is going to indicate what happens here. So once we multiply by 1/2, sorry about that little bump there, but hopefully you get the point. It's not a semicircle anymore, right? Because you're multiplying all of those by 1/2, they're no longer equidistant from the center. Okay, so that is basically that. So we can do all sorts of graphs using those shifts. Okay, so next we're going to talk about composite functions. Composite functions is just plugging one function into another, okay? So the notation for this, f circle g of x, sometimes that's just denoted as just simply f circle g, and then you know you're plugging x into that. What that means is we're taking g, it actually reads it backwards, we're taking g and plugging into f. If you remember it this way, I think sometimes this notation confuses folks. If you just think of it as just keep it in order, I think it helps. So g is getting plugged into f. If you just sort of get rid of that circle and put in parentheses, I think that's an easy way to do that. So in other words, what's going to happen here, go back to when we started this section, part 1, we're taking that domain of x values, okay, and we're plugging it into g, okay, and what we're getting over here is g of x. All right, now we're taking those g of x values and plugging into f, and what we end up getting is f of g of x in our range. Okay, so this composite function has a domain over here at x and a range here at f of g of x. Okay, so this whole thing from there to there would be our f circle g of x. So we'll just take a look at this. I think for the most part, you know, you've seen these types of things before. Sometimes people forget the term composite. Composite is something you'll hear me refer to frequently. Composite just means we're plugging one function into another. So if you think of like a composite material as a material made up from other materials. So a composite function are functions that are made up of separate functions. Okay, so A, let's say we want to do, so this is our functions, f of x and g of x. So let's say we want to do f circle g of x. So once again, I'm going to rewrite this in a way that I think is a little bit more intuitive. Okay, so in other words, we're taking g and plugging it into f. So everywhere I see an x here, I'm plugging in g. And there you go. So that is f of g of x. Now we are going to go ahead and simplify here. So this will be 6x squared plus 6 plus 4. So we get f of g of x is equal to 6x squared plus 10. So we'll call that example 1. And this one we'll call example 2. Sorry for going backwards here. Okay, so let's do same functions. Except this time, well, you know what, let's do this. So that's A, and this is B, same functions. Okay, so G circle F of X. So this time, instead of taking G and plugging in F, we're taking F and plugging it into G. So G of F of x. So I'm just reversing this process. So now, everywhere I see an x here, I'm plugging in f. I think it's a good idea to use parentheses when you plug these things in, especially at first. It just saves you making algebraic mistakes. So right here, what we're doing is we're squaring this term. Okay, a little bit of algebra. All right, let's see, that's 9x squared plus 24x plus 16 plus 2. Almost there. Got to distribute this, so that'll be 18x squared plus 48x plus 32 plus 2. And that gives us our simplified version of this. So g of f of x is equal to 18x squared plus 48x plus 34. And there you go. So those are composite functions. Okay, the last thing we are going to talk about are even and odd functions. Okay, even odd functions. Even odd functions is really just a new way to talk about symmetries. So we're really returning to when we talk about different symmetries. So even f of x is even when f of negative x is equal f of x. Okay? So in other words, if I plug in x here and I get the same output as if I plug in negative x, so for instance in a case of a parabola, that would be even. In other words, this is just symmetry to the y-axis. Okay? Y equals f of x is odd when f of negative x is equal to negative f of x. So take x here, negative x, f, and negative f of x. If we take this point here, okay, it's going to end up here. So this is what we call symmetry to the origin. So for instance, with y equals x to the third, not the best graph, but hopefully you get the point. Sort of that diagonal symmetry. Okay. If you ever get confused with odd functions, if you take the point and reflect it over the y, then the x, and it ends up back into itself, that would be an odd function, symmetric to the origin. Okay, so we're going to test this very similar to the way we tested the different symmetries. Notice I don't have symmetric to the, there's no description for symmetric to the x-axis, right, like we did before, because typically those aren't going to be functions. Only in the case of it being like a horizontal line on the x-axis would that be a function. So it's kind of a trivial discussion to talk about a function that is symmetric to the x-axis. Okay, so let's take a look at determining this. Once again, with symmetries in general, don't just rely on the graphs. As I said before, if we take this graph and shift it 0.00001 to the right, the graph will still look like it's even, but it's not. It's not symmetric to the y-axis anymore. So it's important that you look at the algebra whenever we have discussions of even and odd, just like the symmetries of to the x-axis, y-axis, and the origin. Okay, so let's test a function. This is actually kind of a redo of what we did before, so I'm not going to get too bogged down in this. We basically want to always check we start with the original, then we're going to plug in negative x. So everywhere I see an x, I'm going to plug in a negative. Okay? Let's go with example 1. All right, so we want to simplify this. So f of negative x is equal to negative x to the third power and odd power. We'll retain that negative. Okay, so we get something that looks like this. So obviously it's not even, right? So we can see this right here. These would have to be equal for it to be even. Or, excuse me, these would have to be equal for it to be even. So it's not even, okay? These would have to be equal. Then I'm going to test negative of f of x, okay? So that is going to be a negative outside of this entire function. Okay, so simplify this, negative x to the third minus x. Now we have it. This is equal to this. So what we see is this function is odd. Okay, let's do y equals x to the fourth plus 2x squared. Okay. Well, let's write that with function notation. Okay, so once again, we want to plug in negative x. And quickly we see that these are going to be the same because we're raising both of these to a even power. So this would be x to the fourth plus 2x squared. It is the same as this, so this is an even function. Now, I think you quickly see that this isn't going to be an odd. You still do want to check it because there are examples of functions that are both even and odd. So that's something. Well, I guess they're trivial, but it is possible. Okay, so let's do the negative f of x just for the sake of checking it. And of course what we see is that these are not equal, so it's not odd. If you do have a scenario which will come up where none of these are true, this isn't equal to this and this isn't equal to that, then it's neither even nor odd, which is actually most of the functions are neither even nor odd. So that's it. So that's our prerequisite section 3, part 2.